Welcome. In this video we begin section 2.5, Contradiction and the Pigeonhole Principle. Today we will look at proof by contradiction, and in a later video we will see the Pigeonhole Principle. Before we begin proof by contradiction, here is one other proof technique. Maybe we could call this proof by intimidation. I will not take time on this, but something for you to consider. Alright, proof by contradiction. A simple example. Here's our claim. If an integer n has the form 3k plus 1, then n does not have the form 9q plus 5. Why is it impossible that a number n should have these two forms simultaneously? So let's see. So to prove this, I start by assuming that the claim is false. Then there are integers k and q such that n equals 3k plus 1 and n equals 9q plus 5. So if that's the case, then I can set those equal to each other. 3k plus 1 equals 9q plus 5. Let's move the variables to the left and move the numbers to the right. I can factor a 3 out of the left, and I get 3 times k minus 3q equals 4. Divide both sides by 3. And now something really strange is happening at this equality. Do you see what the problem is? The problem is that the left-hand side, k minus 3q, is an integer by closure, but 4/3 is not an integer. Therefore, our assumption was wrong. Do you see what happened? We assumed that the claim was false, and under that assumption, if the claim is false, then I can logically proceed until I get to a claim that is clearly not true. Since I ended up with something that's not true, I must have made a mistake earlier on in the proof. And I traced my steps backwards. I come up and I realized that the place where I made the mistake was this assumption, assuming that the claim was false. In general, proofs by contradiction have this kind of form. A claim is made that we wish to prove. To prove the claim, I start by assuming the claim is false. Then, under this assumption, I show that an impossible situation arises. Well, we then conclude that our assumption was wrong. That is, the claim must be true. It's kind of a funny roundabout way of proving a statement, but it's very effective and often leads to short proofs. Here's another way of saying that same thing. True statements can lead only to true statements. So, if we end up deducing a false statement, we must have started with a false statement. And by saying we started, that is the assumption. That assumption must have been false. Here's a problem for you to practice. Here's our claim. If a is an integer, then a plus 1/2 is not an integer. That seems like a very reasonable statement to make, right? Well, if the claim is false, then what is true? What will be your assumption at the beginning of the proof? And how does this lead to an impossible situation? Pause and try. Pause the video, work out your solution, and then start again when you are ready to check your work. Let's see. Proof. Assume that a is an integer and a plus 1/2 is an integer. Look what I'm doing here. I'm keeping my hypothesis, but I'm negating the conclusion part. This claim is set up in the form P implies Q. If a is an integer, then a plus 1/2 is not an integer. And do you remember how we negate an implication? The negation of an implication is P and not Q. So this is the form of the assumption that I'll make. A is an integer and a plus 1/2 is an integer. Okay, so under that assumption, a plus 1/2 equals b for some integer b. Let's subtract a from both sides. 1/2 equals b minus a, and I'm in the same situation from the previous proof. 1/2 is not an integer, but b minus a is an integer. They can't be equal to each other. And so this is the contradiction that proves the claim. Thus, if a is an integer, then a plus 1/2 is not an integer. Famous example number 1. There are infinitely many prime numbers. This is an ancient result. This is due to Euclid. And he starts the proof by assuming that there are finitely many primes. This is how he assumes that the claim is not true. Assume that there are finitely many primes. Okay, well then let's just list them out. P1, P2, P3 up through Pk. Suppose that these represent all prime numbers. There are no other prime numbers beyond these. Now, this is where Euclid gets very clever. He says, create the really big number n, which is the product of all the prime numbers plus 1. So that's a very big number, and certainly this n is bigger than any of the existing primes. And then Euclid deduces two interesting statements. First, he concludes that n must be divisible by some prime p sub I, and also he deduces that n can't be divisible by any prime p sub I. And there's our contradiction. Now, I'll give you these reasons, but this is where the contradiction occurs. He says, simultaneously, n must be divisible by some prime pi, and n can't be divisible by any prime pi. And so, what are these reasons? How about this first one? Why must it be the case that this big number n must be divisible by some prime p sub I? Well, this n is composite, so it is a product of primes. Now, I do know it's composite and isn't actually one of these other primes, so because n is bigger than all of the primes. Since n is bigger than all the primes, n is composite, and every composite number is a product of primes. Okay, so it's a product of primes, so this satisfies the claim. N must be divisible by some prime p sub I. All right, how about the second claim? N can't be divisible by any prime. Well, n divided by p sub I leaves a remainder of 1 because of the form of n. You see, this first term, p1 through pk, that is a multiple of p sub I. And then I have a plus 1 at the end. So if I were to take this n and divide by some p sub I would have to have 1 as a remainder. So these two statements together provide the contradiction and prove the statement that there are infinitely many prime numbers. Hey, this is pretty cool. That is a great result. And it's something that is easily proved using contradiction. One more famous example, the square root of 2 is irrational. This is also a result due to the ancient Greeks, the Pythagoreans in particular. The claim is that the square root of 2 cannot be written as a over b, where a and b are integers. Proof. Let's assume that the square root of 2 does equal a over b for some integers a and b. Now, the next step is curious. It tells me a little bit more about a and b exactly. We may assume that the fraction a over b has already been reduced to lowest terms. So in particular, a and b are not both even. When I write a fraction, there are lots of ways I can write an equivalent fraction, right? 2/3, 4/6, 20/30. So basically all I'm saying is, let's just choose our variables a and b so that the fraction is already reduced into lowest terms. A and b have no common factors. Observe that if I square both sides, that a over b squared, that equals 2. And now I want to show that this implies a and b are both even. So there is a useful lemma that if n squared is even, then n is even. We proved this earlier. Oh, and by the way, lemma, that's a great word. A lemma is just a result that is maybe a small result, maybe not so interesting on its own, but it is used to help prove a much larger result. So we want to show that a and b are both even, and I might use the fact that if n squared is even, then n is even. And I'm going to end up with a contradiction. Why? So I am leaving these steps up to you. At this point, pause the video, try your best to finish out this proof, see what you can do, and then start up again when you are ready to see the answer. Alright, let's give this a try. So I'm at this point where a over b squared equals 2. So let's square that quantity and solve for a squared, and I end up with a squared equals 2b squared. Consequently, a squared is even. So now I can use the lemma. By the lemma, a must be even. A equals 2m for some integer m. So look at this now, 2b, which is a squared, can be written as 2m squared, which is 4m squared. So I have 2b squared equals 4m squared. Divide both sides by 2. B squared equals 2m squared. So b squared is even. And then again, by the lemma, b must be even. So I concluded a must be even and b must be even. But wait a second. That's a contradiction. A and b can't both be even. Here we go. So in particular, a and b are not both even. So I've actually created a contradiction where it contradicts something earlier I said in the same proof. Thus, the square root of 2 is irrational. There are different ways that you can have your contradiction arise. You can have an equality that clearly can't be true, like an integer equals a non-integer. You can have two statements that are in opposition of each other, like I did in the proof that there were infinitely many primes. And we can have a contradiction like this, where maybe there's an earlier statement in the proof that ends up getting contradicted. So lots of ways that contradictions can arise. And this is a good place to stop in our discussion of contradiction, because these two results are really fantastic results. They are deep and they are accessible at the same time. And the proofs are easy to get at with proof by contradiction. All right, so that is a good place to stop.